Let's talk about visualizing vectors. This is important as it lets us understand certain concepts more easily or intuitively that would otherwise be difficult. This is the same way as we can have a mathematical function, let's say y equals x squared. That might be difficult to understand, but if you graph it, if you visualize it and see what it looks like as a parabola, it can make certain things easier to understand, like finding where the maximum or minimum of the function is. So visualizing vectors can be very powerful. But let's understand how we can visualize vectors. Well, when we visualize a vector, we imagine that the values inside our vector represent change. So let's take this point at 0, 0. Let's say this is where we began. And then we ended up at this point, which is around 2, 3. There has been a change from our first point to our second point. We've changed this much along the x-axis. So our change in x is 2. That's how much we've changed in that direction. And in the separate direction of y, the amount we've changed is this amount, 3 in this case. And overall, we can use this arrow to represent the overall change that incorporates both how much we changed in the x direction and how much we changed in the y direction. And you can see we use an arrow because there's a direction to our change. The length of the arrow is the amount, but where it's pointing, the angle that it's on is the direction. Because we could have started from our second point and went to the first point. But no, we started from the first point and went to the second point, which is why the arrow goes from the first point to the second one. So direction is important with vectors. There's a direction to our change. So our vector, if we think of the first component as the change in our x, how much we've changed along the x-axis, and our second component is how much we've changed along the y-axis, if we use this representation, this vector, our red vector here, would be the vector 2, 3. It represents a change of 2 along the x-axis and a change of 3 along the y-axis. What's important to note about vectors when we visualize them, since they represent change, it doesn't matter where we position the vector. Just as long as the length and its direction remain the same, it's considered the same vector. So this vector is the same as this vector, which is the same as this vector, which is the same as this vector. It does not matter where we position the vector. All those vectors that we just saw are the same one, because they involve the same amount of change along the x-axis and the same amount of change along the y-axis. Now, if we want to find kind of a number that represents our overall change in all directions, we can calculate the length of this arrow, or the magnitude of our vector. So we can take our change in x, we can take our change in y, and as you can see, it forms a right-angled triangle. And we are looking for the hypotenuse, which we represent with this symbol. This here is the length of our vector. And those two bars on either side represent that we're finding the length of whatever in between them. So we're finding the length of vector v in this case. Now, you may recognize that this is a right-angled triangle, and therefore we can use the Pythagorean theorem. And we get this: the length of our vector is the square root of the change in x squared plus the change in y squared. So the square root of the sum of our two components, the sum of the squares of our two components. If we had more than two components, we simply just add them to the equation. So if we have 3, our dimension of our vector is 3, we add a delta z squared. How about vector addition? Well, remember, vector addition is defined as adding all the corresponding components. So we would take, if we're adding the red vector to this purple vector, we would first take the first component of the red vector, which is its change in x, and we would take the corresponding component of the purple vector, which is its change in x, and combine them. And then we would take the change in y component of our first vector and the change in y component of our purple vector here, and combine them. And where we end up, from where we started to where we end up, is the overall change. And this is the exact same thing as if we had took our red vector and placed our purple vector on top, and then went from the start of our first vector to the end of our second vector. That white vector is the addition, or is the sum of our red vector and purple vector. So visually speaking, what you can do is you take your first vector and attach on to the end your second vector, and then connect from the start of your first vector to the end of your second vector. And that is how you represent visually the sum of two vectors. With multiplication, the same thing. You take your vector and you add it on to the top as many times as has been specified. So if you want to multiply your vector by 3, you take your vector and it becomes 3 times its original size. This is also called scaling. How about if you have a negative, if you're multiplying by a negative value, say -1. All the negative does is reverse the direction of your vector, because it flips all the components. So this vector will become this one. Same magnitude, just different direction. What will become important is understanding how to construct a parallelogram with vectors. Again, the red and purple vector don't have to start at the origin. They can be moved and shifted around. And if we duplicate some of these vectors, we can use them to construct a parallelogram. If we take the red vector and we duplicate it and move it over here, and we take the purple vector and duplicate it and move it over here, we can use these two vectors to construct a parallelogram. And what might be worth thinking about is if there's any cases of two vectors where we couldn't construct a parallelogram. Or perhaps there's a case where we would construct a square or a rectangle with our two vectors, right? Which are cases of parallelograms, but are kind of a special case. So something to think about going forward.